Our learning objectives for today are to find values of trigonometric functions based on the unit circle and to use the properties of periodic functions to evaluate trigonometric functions. Circular functions. A unit circle is a circle with a radius of 1 unit centered at the origin on the coordinate plane. Both cos theta equals x and sin theta equals y are functions of the angle theta. Because they are defined using a unit circle, they are called circular functions. An example are the pedals on a bicycle, which rotate as the bike is being ridden. The height of the pedal is a function of time, as shown in the figure. Note that the pedal makes one complete rotation, in this case every 2 seconds. The two functions defined on a unit circle are the sine function and the cos function. Sine theta equals the y coordinate and cos theta equals the x coordinate. We can see on the diagram here of the unit circle that the x-axis is the 0 angle and the angles go in an anti-clockwise direction, 90, 180, 270 and all the way around to 360 degrees to complete a whole circle. Let's look at an example now of how to actually define or find the angle for sine and cosine functions. The terminal side of angle theta in standard position intersects the unit circle at the point p equals a half and y equals root 3 on 2. So in this case we have p of a half is the x coordinate, so x equals a half and y equals root 3 on 2 will be this point on the unit circle here. So what angle, find sine and cosine given a point on the unit circle? We are actually trying to find the angle between the x-axis and this point, with a line defined by this point that you're given. So in this case, cos of theta equals 1/2, that's the x-coordinate, and the sine of theta equals root 3 over 2, that's the y-coordinate. Now let's practice on an example. You can maybe stop the slide here and make an attempt to work out this solution for yourself. And we'll be back shortly to look at the solution. Okay, we have terminal side of an angle theta in standard position intersects the unit circle at a point P. X equals 3 over 5 and y equals minus 4 over 5. Find cos theta and sin theta. So P of 3 over 5 and minus 4 over 5 has to be equal to cos theta and sin theta. So cos theta equals 3 over 5. And in this case, we can also convert to a decimal, 0.6. And sin theta equals minus 4 over 5, which is minus 0.8. What is this going to look like as a graph? Well, in this case, I've used the Desmos application to graph a unit circle. You can see here that it has a radius of 1, and this is the point down here, 0.6 and minus 0.8. So in this case, what we're looking for is the actual just x and y coordinates of 0.6 and minus 0.8.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom. The first session is always free. We cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. So if you are interested in a free lesson, click the link in the description below, and send us a message now. Okay, with that said, let's get back to our lesson.
Now let's look at a more general concept called a periodic function. A periodic function has y values that repeat at regular intervals. One complete pattern is a cycle. The horizontal length of one cycle is a period. In this diagram, we have a periodic function. In this case, it starts at +1, goes to -1 after 90 degrees, and goes up again until the top a value of 1, and back, which is back to its original position. So that is one full cycle from +1 to +1, and that takes a length of 360 degrees. Now let's look at an example of determining the period of a periodic function. If you look at the diagram on the right, similar to the last slide that we had, the function starts from +1 and goes to -1, and then stays at -1 for a period and goes up and down to -1 again, up to 1. And so it's obviously repeating, but at a set length. In this case, the angles are given in terms of radians. So we have 0, pi on 2, pi, etc. The pattern repeats at pi, 2 pi, and so on. So in this case, we have, remember, for one complete cycle, it has to return to the same position. So we have +1, down to -1, and back up to +1 again. That length is pi, and then the function repeats again from +1 to -1, up to +1, that's 2 pi. So the period has to be 1 pi. One thing to note here is that it doesn't matter where you start. You can start, in this case, from +1 and go to +1, or you can start from pi on 2 and go to pi on 2, or you can even start from the axis here if you can tell what those points are. It's a little bit more difficult in this case, but sometimes you can even use where it crosses over the x-axis to work out what the period of the function is. Just continue until you return to the same y value that you started from. Now let's practice this concept with a question. Graph the function with a period of 4. So you might want to use one of the graphing packages, or you can just simply use a piece of paper or some graph paper. Graph a function with a period of 4 and come back in a few minutes and look at your solution. Okay, graph a function with a period of 4. So the function with a period of 4 will repeat one complete cycle every 4 units. In this case, I'm just going to assume that the function starts at +2 and ranges between +2 and -2. In this case, I'm going to use something called a square wave function. So it starts from +2 for 2 units, goes down to -2, and then stays on -2 for 2 units to give a function with a period of 4. Now, of course, you can use the kind of function with triangles that we used before, or a sine function, or any kind of shape of the function that you like. The most important thing is that one cycle here goes from +2 to +2, or -2 to -2, is one complete cycle, and that happens every 4 units. Values of the sine and cosine function can also be expressed using exact values. The exact values of sine theta and cos theta for special angles are shown on the unit circle at right. Remember, the cosine values are the x-coordinates of the points on the circle, and the sine values are the y-coordinates of the points on the circle. And the cycle of the unit circle repeats every 360 degrees, or in radians, that is 2 pi. So the period of both the sine and cosine functions is 360 degrees. That's how long it takes for them to repeat one complete cycle. Let's look at some examples of angles using cos and sine functions and using exact values to express those angles. First one we will look at is cos 480 degrees. So 480 degrees is more than one rotation of a circle. So cos 360 degrees plus 120 degrees equals 480. Cos 480 degrees is equivalent to 120 degrees, since the period of cosine is 360. We have cos of 480 degrees then is the same as cos 120 degrees. And using the values from the unit circle from the previous page, we have cos of 120 degrees over here is -1/2 and root 3 over 2. But remember that cosine is only the x coordinate. So the answer to cos 480 degrees is -1/2. For the second example, we have sine 11 pi over 4. Again, we have the period of the sine function is 2 pi plus an extra 3 pi over 4. So sine 11 pi over 4 is equivalent to 3 pi over 4 because the period of sine is 2 pi. So if we subtract that, we have sine of 3 pi over 4. We can look at the unit circle again. 3 pi over 4 is minus root 2 on 2, root 2 over 2 on the unit circle. But again, remember that for the sine value of this angle, it is only the y-coordinate, so it is root 2 over 2 for the solution. Now it's time for you to practice on the two following examples. We have cos of -3 pi over 4 and sine of 420 degrees. Find the exact value of each expression, and we will come back in a few minutes to look at the answers. Okay, so for the solution for the first expression, cos -3 pi on 4 is actually a reverse angle, so going from the x-axis in the clockwise direction, we have cos 5 pi on 4 minus 2 pi, since the period of cosine is 2 pi. Cos minus, again, we'll look at the unit circle here again, so cos of 5 pi over 4, 225 degrees, and we want for the cos function only the x part of the coordinate, which is minus root 2 on 2. For sine 420 degrees, again 420 degrees is 360 degrees plus 60. So sine of 60 degrees, look at the unit circle, we have 60 degrees, half, and root 3 on 2. We only want the y-coordinate or root 3 on 2 for the solution for this problem. Now let's take a look at graphs of sine and cosine functions and how we derive those from the unit circle. The values on the unit circle can also be shown on the graphs of the sine and cosine functions. For the sine function, it starts at the x-axis, so theta equals 0 for a y value of 0. The y value increases up to plus 1 at 90 degrees, returns to 0 at 180 degrees, goes down to minus 1 at 270 degrees, and back to 0 at 360 degrees, completing one full cycle. The cos function, on the other hand, starts at plus 1 at 0 degrees theta, goes down to 0 at 90 degrees, to minus 1 at 180 degrees, back to 0 at 270 degrees, and back up to plus 1 at 360 degrees, completing one full cycle. Remember that the periods of the sine and cosine functions are 360 degrees. So in the examples that we looked at before, sine x plus 360 degrees equals sine x, and cos x plus 360 degrees equals cos x. Let's look at an application now. The end by a Ferris wheel has a diameter of approximately 210 meters. The height of a compartment is a function of time, t. It takes 30 minutes to make one complete revolution. Let the height at the center of the wheel represent the height at time t equals 0. Sketch the graph of the function. In this case, we are going to use the value of 0 for the starting point, so we would use the sine function because it starts from a value of 0. The height of the graph is going to be the radius of the Ferris wheel, so 210 divided by 2 is 105 meters. And the period of the graph is 2 pi over 30 minutes, so pi over 15. I've used a graphing package in this case to give you an idea of what this function will look like. So we're using a sine function starting at 0, going up towards the top of the Ferris wheel will be plus 105 meters. So going from the middle here, say up to the top of the Ferris wheel, so that will be the extremum or maximum height there of 105 meters, coming back down to 0 on the other side. So from the top, back down to 0, going down to minus 105, which will be the bottom of the wheel, and then coming back up to 0, our starting point at the end of the function, and of course repeating again and again.